Hey everyone, welcome to our next section with applications of vectors. So we're going to start off and continue on from our first set when we just talked about what vectors were, talked about how to calculate them with the tip-to-tail method or the parallelogram method, as well as learned a little bit about some of the trig concepts that went into solving some of these vectors. So our next section really implies us taking a look at how these vectors can be applied in these everyday scenarios. So forces and accelerations, they're vector quantities, and using these methods we can then analyze objects that are either in equilibrium or are involved with inclined planes. And that's really our two focus sections. So we're going to start off with equilibrium, and the idea behind equilibrium is that you have a force pulling in one direction and you have the same force pulling in exactly the opposite direction. So when it says here, when all of the forces, the sum of all the forces involved are zero, then the object is in equilibrium. Now, the sum of all the forces have to be in the same plane. So for instance, I have a 15 Newton force here pulling down. I need the exact opposite to happen to have 15 newtons of force going up for it to cancel out. So according to Newton's laws, the objects won't move or be accelerated because there's no net force. And this comes from Newton's second law, where the mass is multiplied by the acceleration. And here's my net force. So if I have no net force, if I have 15 newtons going up and 15 newtons going down, that means that this is zero. Right? If I have no net force, that implies that one of these, mass or acceleration, must be zero in order to get zero for a net force. Well, if I have an object or have a problem, obviously it's going to have mass. That implies that the acceleration must be zero. So, as an example, we'll take a look here. It says three people pull on an object centered in the middle of the picture below, and then what's the resultant force acting upon that object. So we know from a previous video what we can do is we can take a look at this and we can draw these out tip to tail, or we can use the parallelogram method. The tip to tail approach for us is going to be much faster, and so all I'm going to do is I'm going to take our three different lines that are here, and I'm going to connect them tip to tail. So if I connect these tip to tail, it should be able to tell us what the resultant force is going to be. Remember that we always draw that resultant force starting from the beginning and going toward the end. So if I start off and take my 3 Newton force, and then at the end of that I'm going to connect on my 4 Newton force, and then at the end of that I'm going to connect on my 5 Newton force, what we actually see here is that the overall forces, do you see how it closes in? So start to finish here, the net force, I have no line to draw because it's zero, right? I have a closed in shape, I have no net force acting on this object. So basically, what we're saying through this is that these three objects, the way that they are right now, they're in equilibrium. So all of them pulling in opposite directions, they're not going to go anywhere. They're going to be in equilibrium. So when a vector sum of forces on a point is not zero, then a force can be applied that is going to produce an equilibrium, and we call that the equilibrant or the equilibrium force. So let's take a look at this scenario here, where you can clearly see all three points are pointing away with an object, right? They're all pointing in kind of, I want to say the same direction. It's not, but there's no force that's pulling against them per se. So if I were to start and just connect these together, I'd have my first force, and we know that I can take that and I can connect it with my second force, which I can then connect to my third force, and what we see here is I have something that is not balanced. The net force is not zero. So in this case, I know I'm going to have something going here that's going to connect this together. That's going to be my resultant force. And so this idea is right here, right? I have my resultant force that I can then use. So I'm going to use that resultant force to then connect this all together. So resultant force is going to go right there, And I can see that I have my line that's going to be my resultant line. Now, my next one after that means that I have an equilibrium force, and that equilibrium force has to be exactly the same, just in the opposite direction. That's going to bring this object into equilibrium. So I have a resultant force. I also have an equilibrium force that opposes that object and moves it into equilibrium. So remember, the resultant force, all it is it says what direction and how much force is going to be applied from the three forces. The same thing we learned from the last one. And then above, it says a force can be applied that will produce equilibrium. So the force that's applied has to be the same force as the resultant, just in the opposite direction. Okay, 180 degrees in the opposite path. So, taking a look at that, should be able to answer these two little questions. So, if the resultant force was, say, 10 newtons at 143 degrees, what do you think the resultant force would be? Okay, I have a force that's pushing 10 newtons at 143 degrees. Well, the resultant force, remember, has to be the same in magnitude, so the same 10 newtons, and it's going to have to be exactly the opposite of 143. Well, what's the opposite? The opposite is 180 degrees. So, 10 newtons at 323 degrees is going to produce equilibrium. If I had 5 newtons, and I had something that was 30 degrees north of east, then the resultant force can actually have a couple different answers here depending on how you sketch this out. The resultant force is going to be either, let's get rid of that, the resultant force is either 5 newtons at 30 degrees, either south of west, or 5 newtons at 60 degrees west of south. And that only comes about because we know 30 degrees north of east is going to go in this direction, right? So I have a plane right here, and I have my original 5 newtons at 30 degrees, and then we know that the resultant of this is going to go exactly the opposite. So maybe you thought about it going this way and referenced it that way, or maybe you thought about it going down this way and then coming over, right? South of west would be my first one, so this one would be my 30 degrees in here, and then west of south would be my other one, 60 degrees in here, where the two of them will just make a right angle. Either way, I have the same 5 newtons that are there. So, we have an example. A sign that weighs 168 newtons is supported by ropes A and B that make 22.5 degree angles with the horizontal. The sign isn't moving, so what forces do the rope exert on the sign? Here we have kind of a bigger problem to consider or to think about. And so really what we need to do is to understand a couple of concepts here that it's talking about. And we'll work through this one together just to kind of give you an idea of how these problems are constructed or how to visualize them. So basically what we have to draw back from are some prior knowledge. It says that this thing weighs 168 newtons, right? Weight is equal to mass times gravity. So it already gives us the weight, and it's basically saying that this thing is pulling down. It has a downward weight of 168 newtons. It's supported by 2 ropes, A and B, and they each make a 25 degree angle with the horizontal. So the horizontal of our sign. The sign is not moving, and that's really important. If the sign is not moving, that means that it's in equilibrium. So that means that all of the up forces have to equal all of the down forces, as well as all other forces in other planes. So it wants to know what's the force, or what forces do the ropes exert on the sign. So I have this downward force with the weight. That means that A and B, the tension on those, need to be pulling in the opposite directions, right? They need to go away from the sign because it needs to produce equilibrium. So a way that I can start to visualize this now is really that I have these little triangles set up that can come off of A, where I'd have an AX and an AY, and I could have a B that would have a BX and a BY. So using what we used from before in terms of vectors, we can actually kind of set up a scenario here. But really, and what a common thing is that people will tend to say with this problem, and maybe we'll just sketch it out on the side to give a different perspective. We've got two different ropes going up, one's A and one's B. We've got a weight of an object pulling it down. In order for this to cancel out, oh, and I also have an X component and a Y component for each one. So in order for these to cancel out, I need to have the same force going in the opposite direction. It's going to be AY and BY. So we need to figure out, okay, the sign's not moving, it's in equilibrium. The net force is 0. So A plus B does not equal the weight because they're not heading in the same plane. A is going off on a slant, the same with B. So what forces would oppose the weight? So what forces would need to total up so that the weight can be canceled out? And hopefully you're seeing here I've got a downward force of the weight. Well, I have two upward forces from my picture, right? I have both of my AY and my BY component. So AY plus BY must equal the weight. Now, what other forces are here that are acting on? Well, something else I can draw from this as well is that AX and BX are pulling in the opposite direction. They're the horizontal forces, but there are no other horizontal forces in this question. So then AX must equal BX. They have to cancel each other out. Okay, I can use these two equations to then figure out some different information to solve this problem. So let's take a look and see what we can use this with. So we know that AY plus BY must equal the weight and that AX must equal BX. Okay, that's a good starting spot. So using a little bit of trig, we can find AX and BX, right? AX looks like it's the adjacent side to the angle, right? The angles are right there. So I have adjacent and I have a hypotenuse A. So I'm going to set up my cosine value to find this value to see what it is. So the cosine of 22.5 degrees must equal AX, that's the adjacent side, over the hypotenuse, which is A. That means that AX must equal A times the cosine of 22.5. And I can apply the same logic for BX because it's the exact same number. So that means that BX must equal B times the cosine of 22.5 degrees. Well, we know that they're equal to each other. So we know that AX must equal BX, right? From right here. They're the only two forces acting in the horizontal plane. So A times the cosine of 22.5 degrees must equal B times the cosine of 22.5 degrees. And if I divide it by 22.5 on both sides, the cosine of 22.5 divided by the cosine in 22.5, what does that leave me with? Well, that tells me that A must equal B, which is a pretty important concept for this problem. Right? The tension in the ropes must be the same. And that only happens because the angles are identical on each side on A and B. So then let's use that in our other equation. So I have AY plus BY equaled the weight. So using the same logic I used when I found cos, I can do the exact same thing for sine. So AY is going to be the sine value of this because I need to take a look at the opposite over the hypotenuse. Okay, so that's sine. So the sine of 22.5 degrees must equal AY over A. Or really, AY is equal to A times the sine of 22.5 degrees. So AY, A times the sine of 22.5 degrees. Again, using the same logic, I can say that BY must equal B times the sine of 22.5 degrees. Okay, so plus B times the sine of 22.5 degrees. We know the weight was 168 newtons pulling down. So we also know here that A equals B. So really that means that I have A sine 22.5 plus another A sine 22.5, because I'm just going to substitute A for B, sine 22.5 is equal to 168 newtons. So I have 2A sine 22.5 degree measures equals 168, which means now I can divide this by 2 sine 22.5 on both sides. 2 sine 22.5. That means that my 2's are going to cancel, my sines are going to cancel, and A is equal to 168 divided by 2 times the sine of 22.5 degrees. That means that A is equal to 219.5 newtons, and it's heading at 22.5 degrees north of the west direction. Now, I also know that A is equal to B, which means B is going to be the same thing. If I were to take a look at significant digits here, really the only thing I have is a 168 that has 3, and I'm dividing it by a trig function that has 3 significant digits in it. So really, this thing is 220, and if I want to show 3 significant digits here, I'm just going to flip it to scientific notation. 2.20 times 10 to the 3 newtons. And it's heading at 22.5 degrees going north of west. So I have my reading or my bearing. I've got everything that I need for that one, and I know that B is also 220 newtons, so 2.2 times 10 to the 3 newtons, going at 22.5 degrees going north of east. So I have 2 separate measures here that both tell me what the tension in the rope is for A and B. Now what's important to kind of understand or see from here, the original weight of the sine was only 168 newtons. Each rope needs 220 newtons of force to counteract. So 220 newtons of force are needed in each rope to counteract 168 being pulled down. That's because it's at an angle. So I have the X component and the Y component in each one really doing a lot of work in terms of counteracting that 168, right? That 168 is evenly split between AY and BY because they both share the same angle. But that means that the tension in that rope has to be really strong to counteract that 168. In fact, it has to be greater than the weight because the Y components are the only thing keeping this in equilibrium, as well as the X components, but they cancel each other out. So using those concepts of equilibrium, I've got a couple of questions for you to try in the book, and if you have any questions, let me know.